Hi kiddos, here's the spiral review for spiral 21. We're going to start off with converting from radical to rational exponent form. And what we know about this is that we can write something as some kind of an exponent with a fraction if we have some kind of radical. We also know that if we don't have a number as the index, that's a 2. That goes as the denominator. Power on the outside becomes the numerator. And whatever's on the inside goes on the inside of the parentheses here. At that point, the problem is done. Next up, we're going backwards. Same type of thing, but this time we're going to have a radical. The denominator becomes the index. The numerator becomes the power on the outside. And this stuff that's on the inside is going to stay on the inside. So w plus 7z. Okay, for number 5, we're trying to simplify this radical expression. And here I'm looking for things that come in pairs. 343, I'm going to try to divide by something like 7, because I know that's going to work. But you can guess and check until you get there. I'm going to get square root of 7 times square root of 49. And then I'm going to try to make this an even power. So I'm going to take a z out of that. And then we get z to the 6th. Alright, a couple things happen. Square root of 7 stays the same. Square root of z stays the same, so I'm just going to keep those there. Square root of 49 is going to be 7. And square root of z to the 6th is going to be z to the 3rd. For number 7, this is an exponent property 1. Here we're going to multiply those exponents together. We've got power to a power, and that's going to get us x to the 10 over 15. At this point you're done, but if you'd like to reduce that, it reduces to 2/3. For number 9, we have to do this as a rational exponent. You can either use a calculator to get this and convert to a fraction, or you could rewrite this as a radical thing, and that would be the cube root of 64 over 27, and that's squared. Cube roots break up over fractions. That'd be cube root of 64, which is going to be 4. Cube root of 27 is going to be 3. That squared gives us a final answer of 16 over 9. For number 6, we've got to get the weird thing by itself. You can divide both sides by 3, and we get x to the 5 over 3 is equal to 243. And then once we do that, one option would be to raise both sides to a 3/5 power. And when you do that, you're going to use your calculator and get a value of 27. As an alternative, and this is the way that I tend to prefer, we could rewrite this as the cube root of x to the 5th is equal to 243. The 5th root of 243 is going to be 3. So we get 3 is equal to the cube root of x, which means that x is going to be 27 when we cube both sides. Next up, we've got to deal with a exponential or log graph. I'm going to treat the first one with dealing with transformations, and the second one we'll talk about graphing without transformations. Here we have the whole graph moving 2 to the right. So I'm going to have an asymptote to start off with, 2 units to the right. We were also talking about moving up 2. That means that each point is going to move 2 to the right and up 2. So, for example, 1, 0 would be at 3, 2. Except I just completely ignored something else going on here, which is that we have a flip as well. That point is still not going to change because we're going over and up from 0. The one that will change would be 4 comma 1. So we have to be a little bit careful with that. So what we've got to do is move it over 2 so we get our horizontal movement. Because the multiplication happens before the addition, we're going to end up having to flip this first. So it's going to start down at -1 and then go up 2, which is weird because it's going to end up back at the same point that we were just at. The shape of this graph is going to look like this. I'm going to avoid giving you ones that have both a flip and a vertical slide in the same problem for this reason. Okay, I'm going to switch colors for my exponential function. Here we're going to have a horizontal asymptote of +1. I'm going to draw that first. And then I'm going to plug a couple points in. Because I've got just an x in the exponent, let's plug in some easy numbers. So let's go with 0. 3 to the 0 is 1. -2 plus 1 is -1. So we get the point 0, -1. And then I'll plug in maybe, I don't know, 1. -2 times 3 is going to be -6 plus 1 is -5. So we get 1, -5. This would give us a graph that looks very steep, something like this. For number 12, the big idea is that these are inverse functions. So 2 points that have to be on the graph of the log base 2 of x, given y equals 2 to the x, would be 1/4 comma -2. I just switched the x and the y. 32 comma 5, I just switched the x and the y. Or 128 comma 7, I just switched the x and the y. For number 13, we're going to convert this from log form to exponential form. This is using the relationship that logs and exponents have, where you have the log base b of a is equal to that exponent, and b to that exponent is equal to the argument inside the log. Okay, let's do the converting. So we're having z to the x is equal to 2w. At that point, we're done. For the next one, we're going backwards. Here we've got b, e, and a. So we've got log base a of c is equal to bx. For number 14, we're evaluating logarithms. That means that we're trying to figure out what this would be equal to. Here we've got base x to the e is equal to x to the 3. That means that e must be 3. For the next one, we've got same setup. So 5 to the e is equal to 5 to the x plus 1. That means that e must be x plus 1. In both of these cases, we're using the fact that these are inverses of each other, and that if you use log of the same base, you undo the exponential expression. We haven't talked about that from the algebraic perspective, but we can kind of see that happen when we do problems like this. For number 15, I'm going to do the second one. We're condensing. I'm going to do this in 2 steps, although you might do this in 1. I'm going to use my powers property to make the numbers out front powers. So we get log base 2 of 5 to the 3rd plus log base 2 of x to the 5th. And then if I'm adding, it means I'm multiplying on the inside. So we get log base 2 of 5 to the 3rd times x to the 5th. Looking at number 16, I'll do the top one. First thing I'm going to do is break this up over the division. That means I'm going to subtract. So we get log of 4x minus log of y to the 3rd. Then each of these has something I can break up. We've got multiplication in the first one. That's log 4 plus log x. And then we've got a power in the second one. So minus 3 log y. For number 17, we're going to solve these equations. This is kind of the easier form of the things we were looking at last week, where we're going to convert these to be the same base. So here we've got 8, which I could write as, I guess either 8 or 2 might work. So let's do 2. 2 to the first is 2. 2 to the second is 4. Okay, I got that one. 2 to the third is 8. I got both. So 2 to the third, x minus 4, is going to be equal to 2 squared, and then 2x plus 1. Since the bases are the same, I can now take the exponents and make an equation. 3x minus 12 is equal to 4x plus 2. I'm going to bring the 3x to this side, the 2 to the other side, and I get x is equal to negative 14. On this side, we're solving exponential and log equations using the relationship between exponentials and logs. I'm going to try to get this part by itself. I'm going to add 5 to both sides first, and we get 4 times 3 to the x is equal to 16. I'm going to divide by 4 to get 3 to the x is equal to 4. There's no number that makes that work that I know, so I'm going to convert this to a log, and we get log base 3 of 4 is equal to x. At this point, we're done. For the next one, this is the thing I'm trying to get by itself. We're going to add 5 to both sides. We get 6 log base 10 of 2x plus 1 is equal to 12. We could divide both sides by 6, and we get log base 10 of 2x plus 1 is equal to 2. Now I'm going to convert this to to exponential form, rather. Here's my base and my exponent. So we get 10 squared, b to the e, is equal to 2x plus 1. That's 100. Equals 2x plus 1. If I minus 1, we get 99 is 2x. And 99 over 2 is equal to x. And then finally, we're in our new section, which is exponential log models. The first part's asking us to do some interpretation. That means that you're going to have to figure out what these numbers mean in the context of the problem. This is talking about the per capita gross domestic product of the U.S. in thousands of dollars is a function of years since 1950. So we're going to start with G of t. This would be the total based on this problem. So that would be the per capita GDP at year t. The number 11, that's my starting amount. That'd be the per capita GDP in 1950, because that's when we're starting. And just to be clear, that would be $11,000, because we're talking about thousands of dollars. 1.022, that's my growth rate. And I'm going to kind of break this down to look at this as a percent. So I know this is 1 plus 0.022. That means we're looking at 2.2% growth. T is going to be the years since 1950. And then the last part of this is what would it mean to plug 65 in for T? Well, that would be 65 years after 1950. So it would be 1950 plus 65, which would end up being 2015. For number 20, we're dealing with one where you have to create your own model. So I'm going to go piece by piece in this. So since 1991, that's going to be based on T. There are a couple ways I can write that. I tend to write that as T and just kind of think through that. 60 patents granted in 1991, so that's my starting value. I'm going to label that P. Each year, the number of patents has increased by 20%. That means that my rate is going to be 1 plus 0.2 for 20%. And each year, that tells me that my K is going to be 1. This isn't every 5 years, this is every single year. So, we have a model for this now. A is equal to 60 times 1.2 to the T over 1. At that point, that part's done. And then the second part of this is actually plugging that value in. So as of 2019, the trick there is realizing that we can figure out what T is based on this. So that's going to be 9 plus 19. T is 28. Okay, let's do this up. So we get A is equal to 60 times 1.2 to the 28. And when we do that, we get a value of 9890.67. So that means that we've got about 9890 patents.